much for the invitation and for the introduction. I need to update that bio because it's almost 10 years now that I've been at Google. So it's time flies. Yes, really happy to be here and present this work. I'm happy that Prakash and Tyler, who are also authors in this work, are able to make it. So I assume everybody can see my slides here? Okay, yes. Great. So the title is not the title of the paper. This is a title that kind of summarizes how I've organized and focused my research in reinforcement learning, at least for the past few years. And this paper is very much in line with that focus. So I assume everybody here, given the name of the reading group, is familiar with reinforcement learning, where we're trying to find policies or behaviors that can maximize the accrued rewards over the lifetime of an agent. And we do this by taking actions in an environment and exploring. And of course, we all know this pretty well. And as we all know, we've seen some really great successes with deep reinforcement learning over the past 5 or 6 years, from beating world champions at really hard games to flying stratospheric balloons or placing chips more optimally for even more machine learning. And this really only happened over the last 6 years. So if you weren't familiar with the field, you might think, well, deep reinforcement learning is kind of a new thing. But if we look at the history, well, we can look at the sort of the canonical textbook, the Sutton and Bartow reinforcement learning textbook. And although this was published in 2018, that's the second version. The version I used was published in 1998. And Sutton and Bartow actually came up, if you read the book, you see that they came up with the idea for writing this book in 1979. And really, the ideas that they were building on were already around for quite a while before then. So reinforcement learning as a concept has been around for a really long time. And so part of my research is focused on trying to continue the advancement of reinforcement learning, but also understand what's making it tick so well in recent years. So just a very brief primer, just to get the background out of the way. We're dealing with an MDP where we have a set of states, for instance, these grids in this grid world, an agent in yellow that can choose from a set of actions. And these actions move the agent around the states in the environment. And those transitions are given by a transition function P. And there's a reward function that sort of implicitly induces the behavior that the agent is trying to maximize. So in this simple example, the agent's trying to reach the green cell at the top right while avoiding the puddles in blue. And so initially, the agent in reinforcement learning, what we assume is the agent doesn't know how this environment works. And so the way it learns about the environment is by taking actions and sort of accruing experience and using this experience to update what we call its value function. So in this case, the Q function, which is a function of state and action. And as you probably all know, this is a recurrent function a recurrence that's built up of the immediate reward. So the reward that the agent receives when performing action A from state X, and the expected sum of discounted rewards in the future. And this is summarized by the function Q. So this is why it's a recurrence. So there's the Bellman update that we call to update this estimate, and the agent, as it interacts with the environment, it continues updating its estimates, and from its estimates of Q, it can extract a policy or how to behave. And once it gets a good enough estimate, then it gets an optimal or near optimal policy, as we see here. So it knows how to act in the environment. And of course, the goal of reinforcement learning, or one of the main goals, is to design algorithms such that the agent can find these Q functions, or at least find these policies so as to act in a near optimal way in an unknown environment. So that's all fine, but with the problems that are mostly of interest nowadays, at least in the real world, have very large number of states. And so if we're dealing with a simple toy environment like this, we can store all the states in a table, and we can keep all the Q values in a table. And so whenever the agent has an interaction with the environment, we can apply the Bellman update to that particular state and only affect that state. And that's fine. And so we can maintain this in a table and continue looking up the values in that very precise and contained way. But when we're dealing with very large state spaces or even continuous state spaces, we can't store these things in a table. And so what researchers typically do is, instead of dealing with the ground states, we deal with features of states. And for the rest of the talk, I'll call these phi of x. So these are features that may be learned or may have been given to the researchers for their task. And then what we do is we apply a function approximator psi to these features of X, and that will become our approximation of Q. Which is what we're interested in. So if you're dealing with linear function approximators, then your psi will simply be a set of weights, and you take the dot product of that with your features, and that gives you your estimate of Q. So this is all great. The problem is when we are interacting with a system like this and we receive a new experience that the agent wants to incorporate into its estimates, we can apply the Bellman update. But now instead of restricting the update to that one state, because we're using these state features, we end up affecting many states around the state in question, X. And this neighborhood is really given by the state features that we're using. And so this makes it problematic because we no longer have these sort of precise and contained updates. So the part of the power of how we're getting these reinforcement learning agents to do such complex and difficult tasks is by the use of deep networks. And this was really brought forward in the DQN paper by DeepMind back in 2015, where they applied deep networks to playing Atari games. So they used convolutional nets, which basically are great for images and pixels, for extracting important features. And they feed these convolutional nets through some fully connected layers, and then at the output of the network, they get estimates for the Q values. So this whole network becomes the psi that I'm mentioning here. And this is how they were able to achieve their state-of-the-art performance. And so they demonstrated that their trained agents could perform better than humans in the vast majority of games. And this really kickstarted the field of deep RL research. And of course, there's been many new improvements since then, and DQN is now kind of considered an old agent, and there's many improved and better agents. So back to our function approximator, this is kind of summarizing my focus of my research. So I'm focused on two things. One is learning representations, and this is how do we build these features phi that I'm mentioning. And the other is how do we understand these deep networks? And this is dealing with these function approximators psi. And the combination of these two is what gives us our estimates for Q, which is how the agent learns to interact. And so deep nets, the approach I'm taking there is very empirical, because the theory is really hard to go beyond linear function approximators, and we're not using linear function approximators when we're dealing with these large problems. So it's taking a very empirical approach. And on the left-hand side, in learning representations, that's where this work falls in, and so I'll be focusing on that. So the problem we're dealing with is we have a set of unstructured states listed here in red, and we're trying to find a mapping psi that maps those states into, for instance, some type of function we're interested in, such as Q. And so we want to learn that mapping. But as I said, when we're dealing with very large states, we don't deal with the raw states, but instead we deal with features of states that structure, ideally they structure the states in some nice manner. And so then when we apply our function approximator to the structured states, we still get an estimate of Q, but hopefully we're doing it in a better way. So we can take our unstructured states and let's consider two states, X and Y, in this unstructured space. When we apply our state features, this might move X and Y around, and maybe they're nearby now. And so what we're interested in is if these two states are nearby in their structured representation, are they still nearby in this function of interest? So when we apply our function approximator of psi. So a bit more formally, what we want to know is if we have some distance d for these structured representations, and note that the distance is between the features of the states and not the distance between the raw states, does this distance tell us something about the difference in the function of interest, in this case, the Q values? More formally, what we're interested in is understanding whether we can provide upper bounds on the difference in value functions by the distance between these features. And so obviously the natural question is, what is a good distance to be able to structure these states in this manner? So one kind of natural, at least to me, option would be by simulation metrics. And this is something that many of you have likely heard of, given that Prakash has been visiting you. So the idea with by simulation metrics, I'll sort of explain how we construct it, is we start with some initial estimate of our metric D, let's say D0. And we're going to apply this update operator TK. And so the way TK is applied is we're going to look at the difference in immediate rewards under some action A, which I'll come to in a little bit. So we're going to take that difference of rewards and we're going to add it to the Kantorovich distance between the transition functions under that function A. Some of you may know this as the Wasserstein distance, but if you've heard Prakash speak, you'll know that that's the wrong term to use, and you should use Kantorovich. So we add these two, but we also discount this Kantorovich distance by the gamma factor. It's the same gamma factor that we use in reinforcement learning when describing the Bellman update. And so the action that we choose is the action that maximizes this sum. And this is how we define the update operator T of K. And so when we apply this, we're going to get a new estimate of our metric, and we'll call this D1. And then we can do exactly the same thing. We have D1 and we can apply TK to it, and we're going to get D2. And we can continue applying this update operator iteratively, and we can prove that this will actually converge to a fixed point as we apply it towards the limit. And we're going to call this fixed point D of tilde, and this is the bisimulation metric. And what's nice about this is that this bisimulation metric provides an upper bound on the difference in optimal values between the two states in question. And this is that upper bound that I was mentioning before. So this is pretty nice because now we have exactly this sort of neighborhood mapping onto neighborhoods from the structured representations onto the function of interest. And so this was introduced in a paper by Prakash, his student Norm Ferns, and Doina Prikup in 2004. The problem with this is that it doesn't tell us anything about other pi. So really, this is only providing a bound on the optimal policy pi star and the induced optimal value function v star. This is somewhat problematic for an RL researcher because, as I mentioned at the beginning, when we're doing RL, we typically don't start from the optimal policy. That's what we're trying to find. So we start with some random policy, and we continue updating this policy as the agent interacts with the environment. So if we are designing the method with which to structure our states using this bisimulation metric, it might not be as informative because it's telling us something about the end goal. But what we really wanted is for it to help us along the way as we're updating these policies. And so there are examples you can construct where actually, if you were to use bisimulation metric, it can actually hurt the learning process, and you can converge to a suboptimal policy. By the way, if there are any questions throughout the talk, feel free to interrupt me. And if not, I'll just continue. Okay, so one thing I introduced in a couple of years ago was this a simple variant of the bisimulation metric, which I call pi bisimulation. And here you can see I got rid of the maximization over the actions. And now the update operator is defined with respect to a fixed policy pi. So there's no more maximization over actions, but we have a fixed policy pi. And what's kind of neat about this is that it does tell us something about other pi's, and we still have the same type of upper bound that we had before. So the pi bisimulation upper bounds the difference in the value functions, but now it's with respect to a fixed policy pi. And obviously pi star, the optimal policy, is a special case of this. So this is nice. Maybe this is opening the door for reinforcement learning. However, we still have a problem with this, and that is that the Kantorovich metric is really expensive to compute. And it's also really hard to do if you don't have access to the true functions P, so the true transition functions, which is typically the case in reinforcement learning. You don't have access to the transition functions. If you're dealing with model-based RL, you might construct an estimate of that, but then your estimates of your approximations of the Kantorovich will be quite biased. So this is quite problematic. If you were to solve it exactly, even you get this big complexity result. And so that's one of the issues that we really set out to resolve in this paper, this MICo paper with Prakash, Tyler, and Mark Rowland from DeepMind. So we're going to define a new update operator, tpi of n, that still kind of has the same general form as we had for the bisimulation update operator. So we have the difference in rewards, and instead of having this Kantorovich metric, which is an optimal coupling between transition distributions, we're going to replace that optimal coupling with an independent coupling. So this might be a part where it might be good to pause in case anyone has any questions about this. If you're not familiar with these types of metrics on distributions, optimal coupling might not mean that much to you. So please feel free to interrupt me. Okay, there's a hand raised. Lucia.
Yes, sorry, I didn't know if I can type my question because maybe typing would be less than speaking, less invasive to the meeting. But just to get the gist of what you are saying here with X and Y and introducing the pi, in my mind, and tell me if I'm wrong, I want to see if the real representation and the abstract representation, they give me both the same rewards. Because if these two representations give me the same rewards, and that's what you're doing in the absolute value there, that means they are close enough.
So this raises an important point. I mentioned that the distances were defined with respect to the features of the state, so phi of x. But I hope you can see my mouse. The rewards here are not a function of the features. They're a function of the ground states. So the rewards that the agent receives from the environment are coming from the true state. So it doesn't matter how you are representing your states or what your features look like. If you're in the same ground state, the rewards will remain unchanged. Now, the transition functions, if you are estimating these from samples and constructing these transition functions, then it depends how you're representing them. So you might represent them as functions of your state features, or you might have some other method of representing them. That's a different story. Here, what really the change we're making from the optimal coupling to the independent coupling is this is kind of the key of the distance we're defining, because this optimal coupling, as I mentioned, it requires you to either have the full transition functions or some estimate of it. Because one of the ways of solving this metric is by solving a linear program, where you have to, if you know linear programming, you have to explicitly express all the constraints and the objective functions. And to do so, you require explicitly knowing or having some estimate of the transition function. For independent couplings, this is much simpler, because now you can just draw independent samples from P of X and P of Y without having to construct a model. And so if I expand this a little bit, basically what we have here is we can draw these two samples, X prime and Y prime, and just look at our current estimate of U. So U is the metric, the distance that we're updating. So rather than going from applying this update operator T pi of K to D, we're applying T pi of M to U. And it's a recurrence, much like we had with the Bellman recurrence and with the bisimulation recurrence. But now, instead of solving some complex linear program, we can just do with samples. And so we can do, if we have multiple samples, we can then just do counts, and we can get this expectation really cheaply and without having to couple these two in any way. So we can just draw, I'll get to a bit more of the implementation, but this independent coupling is quite key to make this work effectively in the situation of online RL, which is where we're dealing with, where we have a stream of experience coming into the agent rather than a full model handed to the agent. And so when we define the update operator in this way, this is what we call the MICo distance. And we can also prove that this, if you apply it iteratively, it'll reach a fixed point. And this fixed point we call U pi. And note that this is similar to pi by simulation in that it's defined with respect to a specific policy pi. So one thing that's quite interesting as we were analyzing this distance, and note that I've been calling it a distance and not a metric, is that it's not a regular metric. So it's what we've coined a diffuse metric. And so a diffuse metric is kind of similar to a regular metric. So it's a mapping from a pair of states to the real line. But here are the axioms that it respects. Well, it respects symmetry, much like regular metrics. It respects the triangle inequality. But the first term, where we typically have for regular metrics, we have identity of indiscernibles, or for pseudometrics, you might have that all identical states have distance 0, but you might have distance 0 between non-identical states. With diffuse metrics, we can have non-negative self-distances. So that could mean that the distance from a state to itself is non-zero. And this seems sort of weird and counterintuitive, but this is where the term diffuse comes from. It's sort of measuring how this process, because if we think of a fixed policy, we end up with this stochastic process, how diffuse is it? So as you execute this policy pi, if you think of sort of unrolling the tree of possibilities, if this tree is very, very wide, it means that there are many possibilities. So there's a higher stochasticity in the transitions. And so that your process is becoming more diffuse. if you have a deterministic MDP where you have a single branch starting from a state, then you basically have a non-diffuse process. And in fact, for deterministic systems, you do actually have 0 self-distances. So there's in the paper and in the blog post, there's some examples to help you come to grips with this if it's something that seems sort of weird. It is kind of weird, but we thought it was a very interesting a theoretical result for this new distance that we defined. Okay, so now that we've defined the MICo distance, oops, sorry. Now that we've defined the MICo distance, how are we going to learn it? Because this is really the ultimate goal for us. So we're going to, obviously we can't express this as a table, as I mentioned before. We're going to represent it using function approximation. And so you can see that now I'm defining the approximate distance, measuring the distance between the state features phi between x and y. And this omega there represents the parameters of the neural network that we're using to approximate the MICo distance. So we've chosen to parameterize it in the following manner. So we have these two terms here. And so in the first term, we have the average of the norms of the representations of x and y. And note that they share the parameters omega that we're using to represent the distance. And then the second term is the angular distance between these two representations. And so this first term, the average of the norms, the reason we include it is because this is what allows a representation to be expressive enough to express diffuse metrics. So this allows us to have non-zero self-distances. If we were to get rid of this first term and only had the angular distance enforces 0 self-distances. And so it wouldn't be expressive enough to represent the MICo distance. And then the second term is, as I mentioned, the angular distance. And this is something that this is where a lot of the kind of experience and know-how with training neural networks comes in. So you can use L2 distance or L1 distance or any other distance you choose between two vectors. But in practice, we did experiment with a few, and it turned out that the angular distance is what worked best. Okay, so now that we have this, how are we going to train it? Well, we have a replay buffer, which is, as most of you know, this is what RL algorithms typically use, where you're storing all your experience in this replay memory, and then the agent pulls mini batches from that replay buffer to be able to train these things on modern hardware like GPUs and TPUs. And so if we pull out a pair of transitions, and I'm omitting the actions because I'm assuming a fixed policy, then we can construct the update or the target for our metric estimate by looking at the difference in rewards and then looking at the MICo distance between the next states. And we're justified in doing this even for stochastic systems because this is an unbiased estimator of that independent coupling that I had before. And so this omega with a bar on top, this is just more of a practical thing. This is using target networks, which if you know DQN, you know what that means. It's essentially a copy of our online network that gets updated less frequently. And this is done to have more stable learning. And so this is what we call the target of our learning objective. And it's really just the update operator that we define for MICo that we have here. So the first term is exactly the difference in rewards. And the second term, as I mentioned, is an unbiased estimator of that independent coupling. So now that we have this target, we can then define a loss, and we can just take the squared loss. So we can look at our target and then look at our estimate of the two states in question. So the target, once again, is looking at this update operator, and our estimate is just looking at the distance as expressed by our representation above. So this is the distance between phi of x and phi of y. And one thing that, and we call this the MICo loss. One thing that was quite important is to use the Huber loss. So the Huber loss sort of saturates large distances. If you were to use just something like mean squared error, what ends up happening in practice is that very large distances tend to overwhelm the gradients. And really what's important is learning the fine differences between states. And so the Huber loss allows us to do this, and this ended up resulting in much better empirical results. Okay, So the way the training actually happens is we take, for instance, a DQN network, and what we're going to do is we're going to split up the network into two parts: the representation and the representation phi and the function approximator psi. So the representation phi we're going to call the convolutional layers. So the output of the third convolutional layer, that's what we're going to call the representation. And the function approximator will be the two fully connected layers at the end. This is somewhat an arbitrary choice, but I think it's fairly well justified. The whole point of the convolutional layers is to really be able to capture the salient features in the pixel inputs that the network is receiving. So if we structure it in this way, then we have what we had before. So psi of phi of x is going to give us our estimate of q. And this is how we will choose our policy. And we obviously, I won't go through the details, but we have the temporal difference loss that you use for DQN or Rainbow or any of these. Temporal difference loss, and this is what is traditionally used for RL algorithms when using deep networks. So what we're going to do in this case is we're going to take any of these types of value-based architectures that have these temporal losses, and we're going to look at pairs of states that we sampled from the replay buffer. Note the networks are identical for both. It's just the inputs that are changing. And so when we look at these pairs of networks, we're going to apply our MICo loss, which I defined in the previous slide, to the representations. So something that's important mentioning here is that the MICo loss is applied directly to the representation, so directly to the output of the convolutional layers. This is, I think, something that I hadn't seen before. As far as I know, it's the first time that we've done this. Typically, when many research papers talk about representations or learning representations, they'll have some representation loss, but this typically has extra parameters to learn the loss. So if you think of something like these world models or dreamers and these types of things, where they essentially are constructing a latent space with which they can do planning, the way they can do this is by adding a reconstruction. So they feed in the pixels, for instance, and then they have a network that reproduces those pixels, and so they have a reconstruction loss. Well, the way they're reproducing those pixels is by extra parameters. They have the inverse of these conv layers to be able to reconstruct the pixels. Now, the issue with that is that when you're doing control, when the agent is trying to figure out what actions to take, it's no longer using those extra parameters, because those extra parameters are not necessary for the control part. In our work, the path in order to get our Q values, which is only going upwards like this, is using every single parameter that is used in a MICo loss. So the MICo loss does not add any extra parameters, which we feel is important, as it's directly shaping the representation. If you add extra parameters, it's not clear whether the extra parameters are absorbing a lot of the information that allows you to reduce the loss. Okay, so these are sort of summarized experimental results. What we have here on the left, these are the standard ALE suite, the 60 Atari games, and this is aggregated scores. So we typically train these for 200 million frames, and these are aggregated over the 60 games, normalized by the human scores, and this is kind of a standard thing to do. I will mention this is using the implicit quantile mean, which is a paper that we also presented at NERPS, and I think we presented this paper at the same reading group a little while ago.
Yes.
So this is a great metric, by the way, very robust, so I encourage you to use it. So when we plot our performance, what we did is we took all of the agents from the dopamine library, including Munchausen IQN, which had recently been published. And what we did is, because our MICo loss, we can simply plug it into any value-based agent. We did exactly that. And I think there was one hyperparameter we had to tune, but we use the same hyperparameter for all the agents. And what we find is that across the board, we get statistically significant improvements by adding the MICo loss. And this is quite challenging, given that agents such as Munchausen IQN are already very good. And so getting gains on top of that is a really hard challenge. It's a different thing getting gains on top of DQN, which is a fairly old agent, but to be able to also improve over Munchausen IQN is quite encouraging. So during the rebuttal process, one of the reviewers was suggesting that we should compare against this other paper by Amy Zhang and colleagues that was published at iClear last year. It's called Deep by Simulation for Control, and it's another way of using by simulation to learn representations. The way they were doing it was a bit, it was using an actor-critic method, in this case, soft actor-critic, and they did have a reconstruction loss, and so they did have these extra parameters. The way they overcame the issue with the Kantorovich metric is that they assumed that their transitions were Gaussian, which is a fine assumption for things like Mujoku, where it's very, a Euclidean type space. And so if you assume that, then the Wasserstein 2 can be expressed in a nice closed form, and you don't have to deal with these complicated linear programs. So we did try that, and instead, what we did for that paper to compare against that is we took their algorithm and we replaced their by simulation loss, which requires this assumption of Gaussian transitions, and replaced it with our new MICo loss. And what we found is that we got a pretty significant improvement. Sorry, the one where we simply changed the by simulation loss is this purple one here, and this is quite an improvement over DPC, which is here in orange. And if we get rid of their reconstructions, because they required reconstruction and having an approximation of the rewards, and simply apply MICo to plug it into SAC, we get really good performance. So this again was really encouraging because it shows that this loss can be quite plug and play for these types of methods. So there's quite a few things I didn't talk about here. There's an implicit projection that's happening, and what we end up using for control is called the reduced MICo, which we understand somewhat. And with Tyler, Prakash, and Mark, we're still doing a lot of theoretical work to try to understand that even better. But these results are quite encouraging so far, and I'm really excited about where we can take this line of work. And so just very briefly, some other work in this space. That we published last year. We did a survey, kind of a survey paper with Charlene and Mark, on looking at metrics for RL. And this is before we had introduced MICo, so it's not in that paper. And with Rishab, who also spoke here, we also have this other metric idea that's looking at distances with respect to policies, to optimal policies. And this is really meant for multitask settings. So when you have environments that are drawn from a distribution, how can you get good generalization? Yeah, so the paper, the link is here if you want to check it out, or if you just Google MICo archive, it'll show up. I also have a blog post where there's an interactive widget that you can play with to get more familiar with diffuse metrics. And yeah, happy to answer any questions if there are any, and thanks for inviting me and showing up.